So let's start our discussion on denoising score matching generative models. To start with, let's look into this picture. So this picture gives us some idea about the underlying distribution of three different class objectives. Okay, so the class of dogs, the class of cats, and the class of cows. So inherent assumption is that all of these classes are following Gaussian distribution, and those are represented by three different colors, that is blue, red, and yellow. Let us assume there is one instance x. Instance is basically a feature vector. Okay, and I want to find what is the probability of that particular instance. To know the probabilistic value of that particular instance, we have to dive into entire data set and find some sort of mathematical formulation of its distribution. Okay, so again, that is not easy because we don't know the diverse aspect of these instances. Okay, as we don't know the density, probability density function of the data set, somehow we need to approximate it. And for the approximation part, let's say P of x is the actual distribution. We need to approximate it to some parameter theta, which will give a probabilistic value, and that value is very close to its actual value, that is P of x. Okay. This is the basic idea. Okay, so now how to choose P theta of x? Okay, so what is the optimal function that can approximate the actual probability in such a way that the values of that approximated probabilistic function is much more closer to its original probability value. Okay, so there are many ways to take the approximation. One such way is like we can have this kind of function as a probabilistic approximator. Okay, so what this function says, in numerator we are having an exponential function. Okay, whereas in denominator we are having one kind of partition function. Fine. Now, why this kind of function? Okay, so again, if we look into the probability, the characteristic of probability, then the characteristics of probability says it should follow. So it should follow basically two main characteristics. Okay, two characteristics. Okay, so the first one will be the values should be between 0 and 1, and the second will be the sum of all will be 1. Sum of all values will be 1. Okay, so is it satisfying that characteristic? Okay, all these values pushing down to 0 to 1, and the sum of all values will be 1. Okay, so yeah, it is following because z of theta is basically the sum of all values basically. Okay, so it is like exponential of minus f theta x divided by sum over all x exponential of minus f theta x. Okay, it is following, right? It is kind of similar to the softmax function, but it is not exactly that softmax function. Why? The softmax function is basically giving distribution over the model output, but here we are calculating the distribution of entire data set. Okay, it's not particular model output. Like whenever you are giving one instances to the model that P of theta x, then P of theta will generate some possible outcomes, and out of those possible outcomes we need to take one best possible outcome. So in that case we will be using the softmax function. Okay. Whereas this kind of function is looking like a softmax function, but it is not doing the same thing. Now let's deep dive into the function. So this function is inspired from the statistical mechanics part, where a well-known distribution called Boltzmann distribution. Okay, so it says that how particles are distributed across various energy states at thermal equilibrium. Okay, So it's basically, this is called an energy function. Okay, energy function. So what does it mean? So it means like, here I have given one example, like if you are having high energy, then you are less likely, uh, you are less likely to be stable. Okay, whereas if you are having low energy, then you will be quite lazy. Okay, so this is what the intuitive idea of this particular function. Okay, so it says that when the energy level is low, you are highly probable that you will be not changing your state, whatever state you are in now. Okay, so this is what the intuitive idea, and here I have mentioned that this is following the characteristic of the probability, that is all values are belonging to 0, like open bracket 0 and 1, and the sum of all these value will be 1. Okay, so now let's look into what is a score function. Okay, so score function, what does it mean? So to start with, let us consider our approximator function, that is exponential of minus f theta x with respect the denominator. Now let's see what does the score function mean. So to start with, let us consider the approximated probabilistic function, that is exponential of minus f theta of x divided by the partition function. So now let's take the logarithm both of sides. Okay, minus log of partition function. So instead of taking gradient with respect to theta, now we'll take gradient with respect to x. Okay, so gradient with respect to x means here also gradient with respect to with respect to x minus f of theta. Here if you take gradient with respect to x, okay, on log of z theta, so this value will be 0, because log of z theta will not depend on x. It is completely independent because it is the normalizing constant. Okay, it is only the function of theta. Okay, so now this particular term we are considering it as a s of theta, that is called score function. Okay, so score function means what is the like approximated score function says. So if we try to learn an optimal f of theta, okay, such that the optimal f of theta will be equal to the underlying score function of the true distribution. Okay, so this is what written over here. So here basically we are having the expected value of the true score function of underlying distribution, or score function of underlying distribution, or true underlying distribution, minus the approximated score function of underlying distribution. So this is what the objective, this is what the score matching objective which we have to deal with. Okay, so what does it signify? So we are taking gradient with respect to x. So what does it mean? So it's like we are having one distribution, and gradient with respect to x says that it will give the direction towards the high density. Okay, so it's like this is what a dog distribution. Okay, this is what the dog distribution, but like it is following the Gaussian distribution. So in Gaussian distribution we will have more number of densities accumulated at mean point. Okay, so here so many densities are present, as it is the mean, and the gradient will say that the direction towards the mean. Okay, go to that direction. If you go to that direction, then you can reach to a point where you will find maximum dog densities. Okay, this is what the inherent assumption of gradient with respect to x. Okay, so here I have given one example, like if this is one instance and I will add the s theta of x, that is the score function, to x, then I will slowly move towards the direction of highest density. Okay, so here is the x, and here is the incremental value of x. The quantity what we increment is basically the amount of score function value. Okay, now this is the raw objective, and this is the objective which we want to achieve. Here you can see that in this objective we do not have any log px term. Okay, so let's see how we can do it. So first of all, we will try to remove the expectation term. So if we want to remove the expectation term, let us consider in a continuous distribution case. So it is integration of px into gradient with respect to x log px minus s theta of x whole square dx, right? So now I will try to remove the square bracket, where I will get p of x square plus dx plus half into p of x s theta of x square dx minus half into p of x 2 into gradient of x with respect to log px s theta of x dx. Okay, let's look into this term, the last term. Okay, can we further simplify this last term? Okay, let's see. Okay, so here 2 and 2 will get cancelled, so I don't need to write the 2.5 term over here. So here it will be p of x gradient of x dx. Now let's apply chain rule. So if you apply chain rule, then you will get integration px. So it will be gradient of px with respect to x divided by px to s theta of x dx, right? These two terms will get cancelled and you will have only these two terms, that is gradient of px with respect to x multiplied by your score function. Now let's recall the multiplication rule of derivative. Okay, so just apply derivative. Okay, so if you apply derivative, then if you apply integration both of the side, then here derivative and integration will get cancelled, so you will left with some sort of limiting value, let's say some y to z, or let's say small z. Okay, and this term remaining. Okay, so here in this case, if I apply this derivative of two multiplications like u and v, if I consider p of x as a u and s theta of x is a v, so I will have, that is p of x s theta of x, that is the original functions, from minus infinite to infinite, because I want to go through all the data samples, minus integration of px derivative or gradient with respect to x s theta of x dx. Okay, so now this thing will get cancelled, because the underlying assumption is like the data set is following Gaussian distribution, and for Gaussian distribution all the densities are accumulated at the mean. If you go away from the mean, the density the accumulated density is basically negligible and tends to 0. Okay, so as you are going through all the data samples, that is minus infinite to plus infinite, the multiplication and sum of the multiplication will get cancelled out. Okay, so what will we have? So it is half of integration gradient of x log px square dx plus half into px s theta of x square dx, and it is like minus of integration of px gradient of s theta of x dx. Okay, so here like you can see that in this case it is not having any sort of s theta of x involved in it. Okay, it is free from theta. So if I want to minimize it, this objective function, for the minimization part, what I need to do, I basically need to take the gradient with respect to theta. Okay, so if I take the gradient with respect to theta, then this term will get cancelled out. Okay, so here the gradient with respect to theta, s theta of x, will get cancelled out. Okay, because it is no s theta. Okay, this term will get cancelled out because it is not having any s theta involved in this like in it. Now we are having these two terms. Now let's rewrite these two terms in a in the discrete probabilistic distribution case, that is half of expectation of x sampled from P of x is theta of x square minus expectation of x sampled from x gradient with respect to x is theta of x. Okay, so here like we can say that this term is not having any sort of log px type of terms in it. Okay, where the log px term is quite intractable and we are not able to simplify, or we are not able to basically get that particular value for a unknown distribution. So now we don't have log p of x anymore in this term. Okay, so it looks like it's a kind of feasible for us to basically model it, because we are only having s theta of x, and somehow s theta of x we can predict the s theta of x, or we can train the s theta of x through a neural network. Okay, so so now so here in the optimal case, both of these terms needs to be 0. So this term needs to be 0 and this term needs to be 0. So what does it signify? Like s gradient of s theta of x with respect to x equal to 0 means, so it is like that it is the some sort of local minima type of setup or local optimal type of setup. So it is the like you are having s theta of x. Now s theta of x is a function, and gradient of x with respect to s theta of x, that is the local minima or local optimal point. Okay, so what does this first term signify? The s theta of x square equal to 0, that s theta of x is basically gradient of x log, okay, p theta of x you can say. So that means that if this is 0 means this is where the data point is present. Okay, if this is 0 means this is where the data point is present, right? Now if you look into the second term, so it is having gradient of x, the gradient of s theta of x with respect to x. So it is basically 2 times gradient of log p theta of x, okay, which is again expensive because it is a Hessian. So somehow we get rid of log px in our expression, but again like we found another expensive term, that is gradient of s theta of x, that will be giving us the Hessian basically. So if you are trying to get gradient of a scalar, then you will end up with a vector. Okay, so basically if your gradient space or the term which you are taking gradient with respect to is a vector, then you will end up with a vector. If you again take gradient, then you will end up with a matrix. Okay, so again it increases the computational cost, right? So like what the other issues basically, so again like we are having the computational expensive term during the training because we are having 2 time gradients. Okay, that is we are end up with the Hessian function, again that is one expensive term. Second one is the limited span coverage. Okay, so limited span coverage means what? Let's say this is a distribution. Okay, so this is a distribution and this is where one data point is present. Okay, and this is where one data point is present. Okay, so it is like, what if the score function of the point which is present over here. Okay, so again it will be difficult to basically scan entire data set. Okay, so again you don't know, right? If this is the x, then you will just compute s theta of x, then x plus s theta of x means what? X will move towards some direction, because you don't know which direction will x will go, because the model is not trained to adapt this type of condition. Okay, so this is the second issue. Okay, now to handle this kind of issue, basically one technique is used called this, it is noise perturbation. Okay, so noise perturbation means what? You are having a data point x. Okay, you add some sort of Gaussian noise of mean 0 and some sigma square, like that standard deviation, right, or sigma variation, okay, variance. So what you will get basically, this is the original data distribution. If you add noise, then it will simply increase the variance part. What is the deviation, standard deviation part? It will scale up the standard deviation part, but it will not change the mean. So here it is the original distribution. If you add noise, then the distribution will look like something like bigger type of spread, you can say. Okay, so so again, like as I mentioned, the sigma is sampled from a Gaussian distribution of mean 0 and variance sigma. Done. So what could be the issue? So issues are again there, but you don't know what is the value of sigma. If you need to add high sigma, then the distribution will completely change and will get overlap with other distribution. Or you need to add some very low sigma. Again, you will left out with some empty spaces where again the problem arises, like you don't know where to move. Okay, so again there is a point to concern. Okay, so what we need to do with the sigma, so we'll look how we can handle it. Okay, so it's like, let's say, what is our original objective? So our original objective was basically half. Okay, this is what the original objective, like. Let me copy it because I don't want to write it again and again. Okay, this is the original objective, but in this objective, instead of x, from now onwards we will use the noised version of x, right? So the original objective will get changed, and here we will have then gradient of x tilde log p sigma of x tilde h theta of x tilde, right? This is what the objective will get changed if we will add noise to it. Okay. So now this is what the objective, and again we will do some sort of simplification. Okay, so now again same thing as we have done previously, that we need to remove the expectation part, and that will end up with integration of px gradient of x log p sigma x tilde with respect to x tilde dx tilde plus half into px into s theta of x tilde, so basically x tilde, right, square dx tilde minus, here half and half will cancel, you will have only px tilde gradient of log px tilde with respect to x tilde s theta of x tilde dx tilde, right? Okay, so now again let's do some sort of simplification. Okay, it's the same thing like what we have done. We just need to apply chain rule over here. You need to apply chain rules, and again you will have like x tilde gradient of x tilde px tilde divided by px tilde s theta of x tilde dx tilde. Okay, this thing will get cancelled, so we are having gradient of x tilde px tilde s theta of x tilde dx tilde, right? Now, like, what does it mean? Like, again, I missed the sigma part over here. Okay, sigma. Okay, so what does it mean? Basically, p of sigma means sigma is the hyperparameter, right? So whenever we are adding noise, we need to have some sort of sigma. What is the spread of that kind of noise? Okay, so now what is like basically p of so this is what our x tilde probability. So if we marginalize it over here, then previously what was there, so it is x tilde condition on x dx. Okay, so previously it was x, then we applied noise on the top of x, so it is what is the probability of x tilde condition on x and expectation over all x basically. So which we will get this one. So just replace it over here. So if you replace this term over here, then you will end up with x tilde integration of px tilde x dx x theta x tilde. Okay. Now simply what we need to do, we will apply again another rule that is called Leibniz rule, which will help us to bring this gradient with respect to x tilde to like we can bring this gradient with respect to x tilde to this position, like probability of x tilde with given x. Okay, so if we do that, then so double integration px gradient of x tilde px tilde x dx s theta x tilde dx tilde. So what we need to do, so let's bring s theta also over here, because h theta doesn't depend on x. So let's do it. So let's change the position. S theta x tilde dx to dx tilde to dx. Okay. So now let's replace this thing with its equivalent chain rule derivative, the original term of that. Like it is like that, the term whose chain rule derivative is this term. So it is again log of px tilde x, right, into px tilde given x is equal to, right. So if you replace this term over here, then what you will get, let me do it over here only. Here I will write t, right. Okay, now this is what our the last term is. Okay, so now we come up with this particular expression, and I will replace the last term with this particular. I want to sample from, that is with respect to x tilde log p sigma x tilde and the L2 norm of it, plus second is like it is expectation of x tilde, right. Expectation of x tilde is sampled from, here you can say that p of x tilde given x s theta x tilde, again it is the L2 norm, right. The last term we will have expectation of x sampled from p of x, and x tilde is sampled from gradient of log p x tilde x with respect to x tilde into s theta of x tilde, right. Okay, so what we need to do here, just add another term, x is sampled from px. There is no point, but somehow we need to merge these two terms, second and third terms. So what will we get? So here it will be expectation, so here half was there, right. Okay, so here expectation of x, so half of expectation of x tilde sampled from p of x tilde x, x is sampled from p of x, okay, s theta of x tilde, so it is L2 norm, minus 2 into log p of x tilde x with respect to x tilde into s theta of s tilde x tilde, right. So this is what the term. So let's do one thing, let's add and subtract this term, expectation of x tilde given px tilde x, x of px gradient with respect to x tilde log px tilde given x, L2 norm of it. Okay, so if you do it, then you will come up with this term, that is half into expectation of x sampled from p of x, x tilde sampled from p sigma x tilde given x, and there we will have s theta x tilde minus log, okay, we will come up with this. Okay, so I am just taking these two terms and did some sort of algebraic adjustment, and I got this particular expression. Now this first term will not contribute anything when you will try to optimize it with respect to theta, because it doesn't have any sort of theta term. So you can consider it as 0, or as it is a constant term when you consider the entire function as a function of theta. So you can just ignore this kind of first term where it doesn't contain some theta term. Okay. So we will reach out to a term where it is looking like this. Okay, now again the bottleneck is that how to compute this part. Okay, because s theta of x tilde, let's like we can do it through a neural network simulation or neural network training, but what about this thing? Okay, to compute this particular term, let's apply the denoising autoencoder concept. Okay, let's apply the denoising autoencoder concept. Okay, so what does it say? So let's say you will have one image. Simple autoencoder concept is like you need to reconstruct that same input with some sort of loss function, and during this reconstruction you need to learn a latent vector. Okay, so what does it the denoising autoencoder do? So it will give x as an input, and in the latent space it will add some sort of noise, and from the added noise latent vector it will try to reconstruct the same image through mean square error. Okay, so it's like the original image, just add a Gaussian noise. Okay, so this is what the p of x tilde given x structure is. Okay, so so it's basically it is saying that p of x tilde x is centered at x, because we are not changing the x, we are just adding some spread around the x. Okay, and the sigma is what again is a hyperparameter to it. Okay, so now what we need to do, let's say let's compute gradient with respect to x tilde of. Okay, so it's like when you will compute gradient with respect to x tilde, so here we will get that rather than computing gradient with respect to, let's do log of it, because it's exponential, right? Log will help us in cancelling the exponential part, so you will be remaining with 1 to sigma square, right, minus log of 2 pi d by 2 sigma square. Okay, now when you take gradient with respect to x tilde, then here you will have gradient with respect to x tilde, and here also you will have gradient with respect to x tilde, and this term will get cancelled because it's a constant term, and you will remain with, okay, you will remain with this particular term, right? Now just apply chain rule over here, and if you apply chain rule, then it's like 2 into x tilde minus x, right, and divided by 2 sigma square, it's minus, right? So again it will get cancelled and you will remain with this part. Okay, so it's something like that. When x tilde is obtained by adding a epsilon noise to it, so what is x tilde minus x? It is the epsilon, so x tilde minus x will be your minus epsilon, so it is the amount of noise you are adding to it, right? So simply if you replace this particular term with the noise thing, so now I will paste it over here. Okay. So here it will be so it's plus of 1 by sigma square epsilon, right, and this is the mean square error or L2 norm, right? Again these things like it is quite intuitive, right? So this is the x and you are adding some noise. Okay, this is the x plus sigma. Okay, so if you remove the noise, then you will again come back to x. Okay, so it is the epsilon is basically a direction towards which you will move when a noise is added. If you subtract the noisy input with the noise, then you will again get your original input. Okay, this is what the objective is. Now it is quite feasible, right? You can have a much more simpler way of optimizing the entire setup, where s theta will be your neural network and epsilon is the noise, the amount of noise which you want to add. Now let us assume that you had a complete entire setup and you just train your s theta. Now the problem comes during the sampling process. So how to sample? Okay, so you know s theta of x tilde, you know. Now how to do it? So it's like simple sampling process. What you need to do, just start with some random point. Okay, some random point, let's say here, and like you need to go, okay, So the amount of move will be decided by s theta of x. So it's simply it is like just ascending your initial point towards s theta of x. Okay, and alpha is basically to add some sort of variation to it. So anyway, it will get converged to to its true distribution after certain number of iterations. But what would be the issue? So the issue would be like, as you know, like you know this s theta is optimal. So wherever you start, you will always reach to this point of like this is the optimal density. Okay, so like there is no point of sampling something new out of it. Okay, so to add some sort of variation, what you need to do, you just explore by some amount. Okay, so this is what your initial setup. After that, you just have some sort of exploration part. Okay, so again epsilon is a noise part. You just add some noise. Okay, some noise which is drawn from, let's say, I, and do some sort of exploration. Then we can get that, okay, you want a dog picture, but different kind of dog you want to sample. Okay, so maybe a dog with small eyes, maybe a dog with some different structure. So in this way you can sample out of this distribution, and this process is called Langevin dynamic process. Okay, so it will allow you to explore the distribution in a much better way. Okay, so again the last bottleneck comes, but what I told you that sigma is a hyperparameter. You don't know what is the optimal value of sigma. Okay, to know the optimal value of sigma, you have to do different kind of experiments. Okay, you have to do different kind of experiment. Okay, so let's say I will fix the sigma to a very large number, then that distribution will get changed. Okay, you will have some overlapping distribution, and it will not a reliable distribution, and it will not resemble as a true distribution. If you have a very low sigma value, then again the distribution will not be explored. Okay, you will not explore the entire distribution. Okay, so if you have a point where there is no field is present, then you don't know where to move. Okay, so to overcome this kind of setup, what you need to do, they propose that let's not fix with one sigma. Okay, let's do experiment with multiple sigma. Okay, so that is called sigma of t. Okay, so in that case our score function will get changed, that is s theta of x delta sigma of t. Okay, so t means at one timestamp you have some small noise, and you train your s theta function, your neural network, with that small noise or perturbation. At timestamp, at a higher timestamp, you may have some higher noise perturbation, and accordingly you train your neural network. So you basically have different setup according to the different timestamps. Okay, so people use the timestamp up to 1000 to get better score matching estimations basically. Okay, so this is what the complete setup for the denoising, score matching estimation or generative model. Okay.